so this video is we try to introduce the Minkowski theorem and try to use Minkowski theorem to prove 4n+1 Fermat conjecture. And in this video, I will not prove the Minkowski theorem, but I will just state the theorem. Okay, so L is lattice. Let me see. L is let me clean. So L is a lattice in Rn. So basically, lattice just you have some AI Vi just spanned, and so Vi is just the vector in Rn. But what we need to assume that AI is the integer. Okay, so this is a set of lattice, and then we can define the first we can define the fundamental, the so-called covolume of a lattice. Basically, you can see that, or I can say that the absolute value of the determinant of basis. Okay, so this is just determinant of the basis. So once you have so this is just V1, V2, Vn, and take the absolute. So this is just the definition of a lattice. Okay, and also so the Minkowski theorem say that for any convex set, so convex means that, or I should say convex. Okay, convex means that if you have any 2 points, x and y, and then you draw a line, you draw a direct line connected, and all of these points must lie in A. So any convex set in A in R, subset of Rn, symmetric with respect to origin, symmetric with respect to origin. So this means if x belongs to A, then minus x belongs to A, has the following. Also okay. So let me see. So basically, this is the first the condition that the symmetric with respect to origin. So symmetric, convex. This is the good condition, and the third is that the volume of the A is larger than 2 to n times d over L. This is the third condition. So for any convex set satisfy this, for any set satisfy these 3 conditions, then so this is the results. Then A must contains a point in L. Okay, so this is the theorem. Okay, so let me explain. Give you the intuition. So suppose I only take the L just be the Z cross Z. So let me say I just take all the integer alone, right? Okay, so if I try to draw a convex set, which has symmetric, and okay, so it seems like if I draw a convex set, it looks like here. Here, then I will somehow contact one point. So this volume is 2 times 2 is 4, right? So intuitively, if I have any set which is convex and symmetric of origin, and if A is the area of the space I take is larger than 4, then it looks like A should contain some points. So this is the intuition, and then you plug in the theorem. They basically say that if volume A is larger than 4, then it must contain the point. So you can try by yourself. Suppose you try to draw some area, and which is your volume is larger than 4, then somehow it must contain some points. So this is the intuition. And indeed, in this case, L is just Z cross Z. So the determinant of this lattice is just 1, 0, 0, 1. So it's 1. And n is 2. So this is the theorem. This is the theorem. Okay, so I already state the theorem. Okay, so what next? What we need to show is that use this theorem we can prove the Fermat 4n+1 theorem. Okay, so theorem Fermat 4n+1. So every prime p which is 4n+1 type. So example is like 5, 13. Let me see. 29. Okay, can be written as x squared plus y squared, which x, y are both natural number. Okay, so this is the definition, the theorem of the Fermat of 4n+1. So I mean, it's somehow difficult to see why Fermat 4n+1 theorem has relationship with the Minkowski theorem. Okay, so now we want to prove. Okay, so the proof is very amazing. That I don't know which guys think of this, but I think it's very interesting. Okay, so we need to use a lemma say that if p is 4n+1, then there exists m in it, which is integer, and p divides m squared plus 1. Or you can say m squared is minus 1 mod p. Okay, so this is the lemma, what we need to show, what we need to use, and I will not tell you how to prove it, maybe in the next some other videos. Okay, so I can take u to be I plus mj. So this is our basis, and the v to be just pj. Okay, so I take L is just span, so L is a lattice. Let me see, lattice. I define L to be lattice spanned by uv. So I can compute the determinant of this L. So it's 1m 0p. So it's p. Okay. And so the integer, the points in L looks like a, I, A, M plus B, P, J. So the points in this just like AI plus AM plus BP, AM plus BP, J. So okay, so this is the points in this L, Okay. Okay, so up to now we have some preliminary. So finally we have lattice, and we will try to build some we'll try to build some what? We try to build some space. Okay, which build some convex set A, which satisfy other three properties, and then we try to say, oh, if this the point which contains must be the answer of the Fermat 4n+1 theorem. Okay, so notice that which omega take any omega belongs to L, and we calculate the norm. What we have a squared plus am plus bp squared. And how about we mod p? So we mod p, what we have is a squared plus a squared m squared. But because the 2am bp contains p, and the b squared p squared contains p. So this is a squared 1 plus m squared p. So this is 0 p. Okay, so which tell you that for any omega belongs to L, then p divides omega squared. Okay, so this is the proof process. Okay, so finally we want to construct convex set A belongs to R2. Okay, so the construction is that A just belongs to be the ball with radius square root of 2 p, square root of 2 times p, and with 0, 0. Okay, so the first is that since ball is convex. Okay, so this is just 0 and the square root 2p, and I draw it Okay, and the second is which is symmetric. Okay, the third, the volume of the ball is just so everyone knows about just pi times 2p, pi r squared. Okay, so which is 2 pi p. Okay, so so you can check 2 pi p is larger than 4 times the volume, the determinant of the lattice. Determinant of lattice is p, so it's 4p because 2 pi larger than 4. Okay, so which tells you that A must contain a point in L. A must contain a point in L. Okay, so this is just follow the Minkowski theorem. Okay, so suppose omega containing A and omega containing L. Okay, so suppose omega is equals to xi plus yj. Okay, and what we have is that p. What we have is what? What we have, the first condition is that since omega belongs to L, so p divides omega squared. Okay, and the second is that since omega belongs to A, so omega known cannot be larger than square root of 2p. It cannot be larger than square root of 2p, which tell you that omega squared is less than 2p. Okay, so here comes the fact that omega is less than 2p and 0, but p divides omega squared. So the only possibility is that what omega is known just p. Okay, so this is the only possibility. Right, this is the only possibility. Omega squared is equal to p because omega is divided by p and omega is larger than 0 and less than 2p. Okay, so which tell you that sorry, I have not mentioned that I have a technical point which I didn't mention. Minkowski said that omega the A contains the non-zero integer point. Otherwise the statement is trivial. Okay, the only possibilities. Okay, so x squared plus y squared equals to p. Because this is just x squared plus y squared. Because omega only contains integer point. Okay, so sorry, L only contains integer point. Okay, so this proved the Minkowski theorem. This proved the Fermat 4n+1 theorem by using the Minkowski theorem. Okay, so I think it's really amazing. So the key fact is that Minkowski theorem proved Fermat 4n+1 theorem. Okay, I think this is good for this video, and enough for this video, and I will see you guys in the next video. And in the next video, we will use the Minkowski theorem to prove the 4 square Lagrange theorem. This is somewhat technical, but I will try to prove it.